So welcome to part 3 of lecture 4. So we're going to take a little bit of a detour in this next part here and talk about how to write proofs. Because when we go into or when you start your homework assignments, I'll be expecting you to write more proper proofs. Now, if you've taken 1C, you would have actually seen some of this before. If you haven't, I just want to give you a quick pointer about how to do this. And so the most important thing that you want to keep in mind is that you have a statement usually, and what you want to do is write a justification for why that statement is true. And I'm going to give you kind of a kind of standard technique in which you find your proof and then what you do once you find your proof. Okay. So the procedure that I'm going to talk about is called working forwards and backwards. Okay. And if you look at most textbooks, most mathematical statements have the form if P, then Q. Okay, so most mathematical statements have this. And what you want to think of is there's a P, which is the hypothesis, and you want to argue forwards. Okay, and so what do I mean by that? Okay, so you want to think about what statements must be true. Okay, and then from Q, you want to kind of argue backwards. Okay, so i.e., what statements must be true to force Q to be true. And the idea is if you know the P where you begin with and you know where the Q is, you want to kind of move forward from the P and move backwards from the Q. And hopefully at some point you'll be able to kind of meet up and then you have kind of your argument that goes from the P to the Q. Okay, so I think I've written that up here. So your goal is to try to meet in the middle. Right, so you want to think about when you're doing these mathematical statements is you're given some hypothesis, right? So this is your hypothesis over here, a bunch of conditions, and you're given some sort of conclusion. And you want to think about, well, from P, I know I can get P1, and from P1, I can get P2, and then I keep going this way. And then you go, well, what do I need to show that Q is true? Well, if I can show Q1 is true, then I can get Q is true. And to get Q1 is true, then I can, if I know that Q2 is true, then maybe I can prove Q1, then I can prove Q. And then, so the idea is you're kind of working forwards this way, and you're working backwards this way, and you want to try to meet in the middle. And then when you meet in the middle, you have your original hypothesis implies the P1, which implies the P2, all the way down to the statement Q. Okay, now, one thing that kind of you're not seeing when you come to a textbook or you come from a lecture is basically all the scrap work. A mathematician, when they do their work, a lot of it is spent, writing on pieces of paper or whatever, typing it up, and they're trying to kind of come up with the argument. And what you're seeing is actually the very nice polished result. What you're not seeing is kind of all of this stuff right in here that kind of like the thinking part. Because when you're doing your proofs, you may go P1, P2, go to P02, and then you may have go up to P4, and you realize, oh, this is not going to help me at all. So you have to kind of backtrack and start thinking about different ways to go. All right, so I just kind of want to illustrate this using a linear algebra example. And so here, I forgot some hypotheses. Let's say I have two subspaces, and I know that one is not, U is not contained in W, and W is not contained in U. And then what I want to show is that the union of those two is not a subspace. Okay, so if you want to think pictorially here, what I'm doing here is I have two subspaces, U and W. U is not contained in W, W is not contained in U. So if I take the union of this, it's not going to be a subspace. Okay, and I kind of want to illustrate, this idea of moving forwards and backwards here using kind of a scrap paper approach, so you can see how this works. Okay, so what you want to do is start thinking about, well, what information do I know? Well, I'm given that U is not contained in W. So what that means is that there is U in U minus W. right? So this is in U, but not W. And so if you're thinking about the picture, you have a little u right here. Okay, and the other thing that they're giving me, oops, I got this wrong, switched around. It's a good thing it's scrap paper. W is contained inside, W is not contained inside of U. So kind of the same argument. There is W in W minus U. So in W but not U. So that means that there's a little guy W over here. Okay, not entirely sure what to do with this. So, but that's just kind of rewriting the P part. So maybe here I'll label the P part right here. This is the P part, and this is the Q part. This is my conclusion, right? So here's my P here, and maybe at the bottom of my page, this is kind of like what I like to do, is put my Q part here, and this is what I'm aiming for is that U union, no, too many U's there, U union W is not a subspace. Okay, and so I have to think about, well, what does it mean not to be a subspace? And I know a lot about when things are not a subspace, so I can actually argue backwards here. Okay, I know it's not a subspace is U union W fails one of the three conditions of a subspace. Okay, well, that's good to know because I can actually think about what each of those conditions are. Okay, so, okay, what are those conditions? I guess I would have 0, so maybe it fails. 0 is in the union, or maybe it fails closed under addition, or maybe it fails closed scalar multiplication. Okay, so now what I want to do is I do have some information about P, and can I use this information to show that if one of these things is true, if one of these things are true, then it fails one of the three conditions, so it's not a subspace. Okay, so let's think about this. Well, U and W both contain 0, so the intersection contains 0. So this part is actually, this holds, okay? This is okay. So this won't work, okay? So hopefully you can see why it won't work because 0 is inside of this, okay? What else won't work? Well, it won't work under scalar multiplication, right? Because if you take something that's in the intersection, or in the union, okay, it would belong to one of them, and then the scalar multiple would also be in the other one. Okay, so this actually won't work since U union W does satisfy this property. Okay, and maybe you don't see that right away, but you could try to convince yourself. I know it's a bit messy, but this is, as I said, my scrap paper. So the only hope we have is to try to show that it's closed under subtraction, fails closure under addition. Okay, well, let's think about this now. We kind of have these specialized U and W. Okay, so we have UW is inside of U intersect U union W is U plus W inside of U union W, okay? And the answer is actually no. No, because if U plus W was in U into union W, then U plus W is in U, or U plus W is in W. If U plus W is in U, then since minus U is also in U, u plus w plus minus u is in u, which is equal to w is in u. And that's a problem, right? Because w was said that it wasn't in u. And finally, if u plus w was in w, then since minus w is in w, u plus w plus minus w, which is equal to u, which is inside of w. Again, it's a problem. So we have that it fails closure under addition. Now this is a mess. Okay, this is a complete mess. And this is not what you want to hand in, right? So what this is kind of like your scrap paper, and you're like, oh, okay, I think all the ideas are here. And what you want to do is stop and write it out neatly. So that's what we'll do in the last part of today's lecture.